And on this lecture, I answer two questions. In the first question, you find out they have this semicircle that is inside quarter circle A or B. The second question, you find out they have this ring shape. So start with the first question. In the drawing, a semicircle that is described by this quarter circle A or B. This is the right angle, A or B is the right angle. Line side OS equals to 400 sinus length. In addition, you know that arc AQ equals to RQB. Again, arc AQ equals to RQB. Its size. Task is to find out the area of this semicircle. So first of all, we define the center of this semicircle. This point is point C. We define the touching point of the semicircle with the quarter circle. This point is point P. We define the radius of this semicircle as R. So CP is the radius of the semicircle that equals to R. Likewise, CQ is also the radius of the semicircle that equals to R. Point S this is point S. This is the point of tendency of tangent OB with this semicircle. So in the next step, we join point C and S together by a straight line. Point C is the center of the semicircle. Point S is the point of the semicircle itself. Therefore, CS is the radius of this semicircle. It equals to R according to our definition. So the radius CS is equals to R. The radius CS is drawn to point S, that is the point of tendency of tangent OB with this semicircle. Whenever you have a radius that is drawn to the point of tendency, then tangent BO will be perpendicular to the radius SC. If BO is perpendicular to SC, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. So, in the next step, we will do a construction. That is to say, from point Q, we will go perpendicular on OB. Again, from point Q, we will go perpendicular on OB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and OB. This point is point M. So we have here three lines PO, three line segments PO, CS, and QM. And those two lines and those two angles, they are equal to 90 degrees plus 90 degrees, it is 180 degrees. Repeat again. Those two angles, well, equals to 90 degrees plus 90 degrees, that is 180 degrees. So the sum of those two angles is equal to 180 degrees, and therefore they must be located between parallel lines. That is to say, CS is parallel to QM. So I can quickly on rule 22. According to rule 22, if the sum of two one-sided interangles is equal to 180 degrees, then they're located between parallel lines. We have two lines, Q, A and B, and there are line C that cuts those two lines, A and B. Those two angles are defined as interior angles. So if alpha plus beta equals to 180 degrees, then it means that A is parallel to B. Again, line A is parallel to line B if alpha plus beta equals to 180 degrees in total. So if we can implement rule 22 in our drawing. One cause in our drawing, as I already mentioned before, the sum of those two triangles is equal to 180 degrees in total. According to rule 22, they must be located between parallel lines. That is to say, CS is parallel to QM, or QM is parallel to CS, according to rule 22. Likewise, the sum of those two right angles is equal to 180 degrees, and therefore those two triangles must be located between parallel lines. That is to say, PO is parallel to CS. PO is parallel to CS according to rule 22. So PO is parallel to CS. So in total, we can find out that QM is parallel to CS is parallel to PO. Likewise, the sum of those two right angles is 180 degrees, and therefore they must be located between parallel lines. There are triangles. The sum of two triangles is equal to 180 degrees. According to rule 22, they must be located between parallel lines. That is to say, PO is also parallel to QM. PO is parallel to QM. So in total, QM is parallel to CS is parallel to PO. So we have here three lines that are parallel to each other. PO is parallel to CS is parallel to QM. And then again, we have in the drawing three lines, QM, CS, and PO that are parallel to each other. And whenever you have three lines or more that are parallel to each other, you can implement the test theorem. Whenever you have three or more parallel lines, you can implement test theorem. So if you have three parallel lines or more that are connected with other two lines, like in this drawing, those three parallel lines are connected together by line segment QP and line segment MO. So here we can implement the test theorem. According to the test theorem, the relationship between the two line segments that are not parallel to each other, that is to say QP and MO, is as follows. P C over CS equals to OS over SM. Again, PC over CS equals to OS over SM. Again, PC over CQ is equal to OS over SM. So now, according to test theorem, the following equation is true. That PC over CQ is equal to OS over SM. So now going, because of the fact that we have three parallel lines that are connected with two line segments, the following relationship exists between the two line segments that are not parallel to each other. That is to say, between PQ and OM. According to test theorem, the following equation is called that PC over CQ equals to OS over SM. So here PC is R over CQ is also R, and is equals to OS, that is 3 according to what is given in the question, over SM. SM is the missing side, so it is. So in total, according to test theorem, the following equation is true. That R over R equals to 3 over SM. R over R is 1. So 1 equals to 3 over SM. Again, 1 equals to 3 over SM. Here we multiply this equation by SM. And we get that SM equals to 3 units in its length. This is the missing line segment SM that equals to 3 units in its length. Actually, this is the line segment SM that equals to 3 units in its length. So, in the next step, so OM in total equals to 3 plus 3, that is 6. In the next step, we will join points O and Q together by a straight line. By joining points O and Q, can they do triangle QOM? Can they do? This is a triangle QOM, it is the right triangle. So here we can implement rule 23 in our drawing. Repeat quickly rule 23. According to rule 23, side triangles that subset on equal arcs are equal to each other. In the drawing we have a circle. This is side triangle AOB. This is equals to alpha degree inside. This is a side triangle COB. That is equals to beta degree inside. So if arc AB is equal to arc CD. Again, if arc AB is equal to arc CD, then those two center angles that subtend on those two arcs, angle preferring center angle UB subtend on arc AB, and center angle COB subtend on arc CD. So if the lengths of the arc are equal to each other, then the center angles that subtend on equal arcs must be equal to each other in their sizes. That is to say, center angle UB is equal to center angle COD. And center angle UB equals to center angle COD, or alpha equals to beta. So whenever you have two center angles that subtend on equal arcs, they must be equal to each other in their sizes. In this case, alpha equals to beta. We can actually implement all 23 in our drawing. Well, in our drawing, it is given us in the question that arc AQ is equal to arc QB. Again, according to what is given us in the question, arc AQ equals to arc QB in its length. Arc center angle AOB, point O is definitely the center of the quarter circle, therefore it is a center angle. Okay. So therefore A point O is the center of the quarter circle, therefore angle AOB is the center angle. So angle AOB subtend on arc AQ. You can see that angle AOB subtend on arc AQ. Likewise, this is angle BOQ, center angle BOQ that subtend on arc QB. And it is given us a question that those two arcs are equal to each other in their length. So arc AQ equals to arc QB. And because of the fact that those two center angles subtend on equal arcs, they must be equal to each other in their sizes. So if the size of this center angle AOB is theta, then the size of this center angle BOQ must be also equal to theta, because they are equal to each other according to all 23. Okay, so center angle AOQ equals to theta, center angle QOB equals to theta also. Theta plus theta is 90 degrees. Again, theta plus theta is 90 degrees, because it is a right angle. AOB is a right angle. So theta plus theta is 2 theta. 2 theta equals to 90 degrees. Two theta equals to 90 degrees, and the angle theta itself is equal to 45 degrees. Angle theta equals to 45 degrees in its size. This is angle theta that equals to 45 degrees in its size. In the next step, we'll focus on this right triangle QOM. This right angle QOM is very easy to see that tangents 45 degrees equals to QM over MO. Again, tangents 45 degrees equals to QM over MO. Tangents in triangle, the right triangle OQM tangents 45 degrees equals to QM over MO. And again, in the right triangle QOM, tangents 45 degrees equals to QM over MO. QM is the missing side, so here it is. So it is QM over MO. MO in total equals to 3 plus 3, that is 6. So if you follow the tangents 45 degrees equals to QM over 6. And again, in total, we found out that tangent 45 degrees equals to QM over 6. Tangent 45 degrees is of course 1, so substitute tangent 45 degrees by 1. So 1 equals to QM over 6. Here we'll multiply this equation by 6. And we get that QM equals to 6 units in its length. So actually, this is the missing side QM, that equals to 6 units in its length. So I write it down in the drawing. QM equals to 6 units in its length. In the next step, we will do a construction. That is to say, from point C, that is the center of the semicircle, we will do perpendicular on QM. Again, from point C, we will do perpendicular on QM. So actually, this angle equals to 90 degrees. And this angle also equals to 90 degrees according to our construction. We'll define the touching point of the perpendicular from point C and QM. This point is point L. So by doing this construction, we created the quadrilateral CLMS. Quadrilateral CLMS. Inside quadrilateral CLMS, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle in total must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral CLMS we have 4 right angles, and therefore quadrilateral CLMS will be a rectangle according to rule 5. Write it down. Quadrilateral CLSM is a rectangle because it has 4 right angles. But we also know that the opposite sides of the rectangle are equal to each other. So in this rectangle CLMS, side CS equals to side LM, but here CS is out, is the radius of the circle, therefore LM must be equal to R units in its length. Likewise, according to the same rule, in the same rectangle CLMS, side SM is equal to the opposite side CL, but SM is 3, therefore the opposite side CL must be also equal to 3 units in its length. What is the length of this line segment QL? From the drawing, it is very easy to say that QL in total equals to QM minus LM. Again, QM minus LM equals to QL. So write it down. QL in total equals to QM minus LM. So QL in total equals to QM. We already found out that QM equals to 6 units in its length. minus Ln. We just find the formula that Ln equals to R. So in total, QL equals to 6 minus R units in its length. This is everything nice and QL, that equals to 6 minus R units in its length. So in the next step, we copy the right hand triangle NQC, this right hand triangle NQC, in your page, and we implement the Pythagoras theorem on this right triangle QLC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a progression from Pythagoras theorem. So actually, this is the right triangle QLC that according to the original law is the right great triangle QLC. According to the Pythagoras theorem, in this right triangle QLC, QC squared, that is the square of the hypotenuse, equals to QL squared plus CN squared. Again, QC squared equals to QL squared plus LC squared. So write it down. So QC squared, that is the square of the hypotenuse, equals to QL squared plus CL squared. The hypotenuse QC is the left side, so QC equals to R, of course. Therefore, QC squared is R squared. QC squared is R squared. And it equals to QL squared. QL is 6 minus R, therefore QL squared is 6 minus R squared plus CL squared. CL is 3, therefore CL squared is 3 squared, that is 9. So in total, actually found out that R squared equals to 6 minus R squared plus 9. Here we open the brackets of this expression and finally get that R squared equals to 6 minus R squared. 6 minus R squared equals to 6 squared, that is 36, plus R squared, minus 2 times 6 times R, that is minus 12R, plus 9. So we found out that R squared equals to, this up to the equation we have 36 plus 9 is 45. And we have also minus 12R. We have R squared on both sides of the equation, so R squared will get cancelled. So in this side of the equation we left with nothing, that is to say 0. So in total 0 equals to 45 minus 12R. Here we add 12R to this equation. And finally we get that 12R equals to 45. Here we divide this equation by 12. Finally we get that the radius of the semicircle, the radius of the semicircle is equal to 45 or 12 units in its length. The radius of this semicircle R equals to 45 or 12 coordinates in its size. Our task is to find out the area of this semicircle. Actually, you know that there are 20 semicircles. Is equal to the area of the circle over 2. That is to say, it is pi r square over 2. So it is pi over 2 times r square. R square is 45 over 12. R is 45 over 12, therefore r square is 45 over 12 squared. So in total, the area of the semicircle, that is the area that we are looking for in this question, equals to pi over 2 times 45 times 45 over 12. 45 or 12 units in its size. So the value of this expression in total is equal to 225 pi over 32. Actually, here we can divide both the numerator and the denominator by 3, and we get that 45 over 3 is 15, and 12 over 3 is 4. So in total, r equals to 15 over 4. And again, that the area of the semicircle in total equals to pi over 2 times r squared. R is 15 over 4, therefore r squared is 15 over 4 squared. So in total, the area of the semicircle equals to pi over 2 times 15 over 4 squared. So it is pi over 2. 15 squared is 225 over 4 squared, that is 16. So in total, in the numerator we have 225 pi. In the denominator we have 16 times 2 is 32. So in total, the area of this green shape, that is the area that we are looking for in this question, is equal to either 225 pi over 32 square units in its size. In terms of numbers, it is equal to 22.09 square units in its size. Repeat again. We have found out that the area that we are looking for in this question, that is the area of this semicircle, equals to either 225 pi over 32 square units in its size. In terms of numbers, the area of this semicircle equals to 22.09 square units in its size. So we finished with the first question. In the next step, I'll present the second question. This lecture. So the second question our task in the second question is to find out the area of this green shape. So in the drawing, we have the right triangle, triangle ABC. Triangle ABC is the right triangle because this is angle BC is the right angle. In addition, we know that side AB of triangle ABC equals to 6 units in its length, side AC equals to 8 units in its length. Inside triangle ABC, we have those two identical circles. Repeat again, our task is to find out the area of this green shape. So, first of all, because of the fact that triangle ABC is a right angle, we can easily find out the size of the hypotenuse BC. According to the Pythagoras theorem, in a right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, in the right angle ABC, according to the Pythagoras theorem, BC squared BC square, this is the square of the hypotenuse, is equal to AB square plus AC square. And again, in this triangle ABC according to the hypotenuse, the following equation is true. BC squared, that is the square of the hypotenuse, equals to AB square plus AC square. The hypotenuse BC is the missing side, so we limit it, so it is BC square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus AC square. AC is there, therefore AC square is 8 squared, that is 64. So in total we found out that BC square equals to 36 plus 64. 36 plus 64 is 100. So in total we found out that BC square equals to 100. Here we take a root out of this equation. Finally we get that BC equals to the square root of 100, that is 10. So the hypotenuse BC equals to 10 units in its length. This is the hypotenuse BC, that is equals to 10 units in its length. In the next step, we define the center of this circle. This point is point P. Likewise, we define the center of this circle. This point is point Q. We define the point of tendency or tangent BC with this circle. This point is point L. We define the point of tendency of tangent BC with this circle. This point is point N. We define the point of tendency of tangent AC with this circle. This point is point H. We define the point of tendency of tangent AB with this circle. This point is point K. In the next step, we join points P and L together by set line. And we will define the radius of this circle as x, because of the fact that those two circles are identical, they have also the same radii. Therefore, the radius of this circle must be also equal to x. So point P is the center of this circle, point L is the point of the circle itself, therefore PL is the radius of this circle equals to x according to our definition. Point L is the point of tendency of tangent BC with this circle. The radius PL is equal to x. The radius PL is drawn to point L, that is the point of tendency of tangent BC with this circle. And whenever you have noticed that you don't do the point of tendency, then tangent BC will be perpendicular to the radius LP. BC is perpendicular to LP, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to all one. Likewise, we join points Q and L together by side line. Again, point N is the point of tendency of tangent BC with this circle. Qn is of course the radius of this circle, equals to x. And according to all one, this angle equals to 90 degrees, and this angle also equals to 90 degrees. In the next step, we implement all 10 in our drawing. Repeat quickly on all 10. According to all 10, if two circles touch each other externally, then the straight line that connects their centers together passes for their touching point. In the drawing, we have two circles that touch each other externally at point P. Point P is the touching point of those two circles. Point O is the center of this circle. Point M is the center of this circle. The straight line that connects the centers together is of course the straight line OM. And according to this rule 10, the straight line OM must pass through their touching point, that is point P. Again, the straight line OM must pass through point P, that is their touching point. OPM is one straight line. Again, OPM is one straight line according to this rule 10. So we can actually implement rule 10 in our drawing. In our drawing, we define the touching point of those two circles. This point is point M. The center of this circle is at point P. The center of this circle is at point Q. The straight line that connects the straight line that connects the centers of those two circles together is of course the straight line PQ. And according to rule 10, the straight line PQ must pass from point M, that is their touching point. Again, the straight line PQ that connects their centers together must pass from point M, that is their touching point. Or PMQ is one straight line. Again, PMQ is one straight line. And because of the fact that PMQ is one straight line, it means that PQ in total must be equal to PM plus MQ. PM is of course the radius of this circle, that is equals to X. Likewise, QM is also the radius of this circle, that is equals to X. So, according to what I said 1 second ago, PQ is one straight line, and therefore PQ PM plus MQ will be equal to PQ. So PQ equals to PM, that is X, plus MQ, that is X. So PQ in total equals to X plus X, that is 2X. So write it down, I should follow that PQ equals to 2X units in itself according to rule 10. PQ equals to 2X. Point M, the touching point between those two circles. So from point M, we draw perpendicular on BC. Again, from point M, this is the touching point, the touching point of those two circles. From point M, we draw perpendicular on BC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point M, and we see this point is point Z. What is the definition of line 7 ZM? What is the definition of this line 7 ZM? ZM is a current tangent. So ZM is tangent to this circle, point M, and ZM is also tangent to this circle, and it's point M. So because point M starts from near touching point. Therefore, ZM must be a current tangent that belongs to both circles. the radius QM that is equals to x, the radius QM is drawn to point M, that is the point of tendency of tangent M with this circle. And now radius that is drawn to the point of tendency, then tangent ZM will be perpendicular to the radius MQ. If ZM is perpendicular to MQ, it means that this angle equals to 90 degrees according to rule 1. Likewise, the radius PM that is equal to x is drawn to point M, that is the point of tendency of tangent ZM with this circle. Now, radius that is drawn to the point of tendency, then tangent ZM will be perpendicular to the radius MP. So this angle equals to 90 degrees according to rule 1. So inside quadrilateral PMZL, we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle in total must be equal to 360 degrees. According to the rule, that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its side. Quadrilateral PMZL has 4 angles, and therefore this rectangle according to rule 5. Write it down. The small quadrilateral PMZL is a rectangle because it has 4 rectangles. Likewise, in this small quadrilateral MZ and Q, we have 1, 2, 3 rectangles, and therefore this fourth missing must be equal to 90 degrees inside, and therefore this quadrilateral is a rectangle only 4, 5 because it has 4 rectangles. So here's 2 small rectangles. Those are the 2 small rectangles that we have in the drawing. What about the big quadrilateral PQ and L? Quadrilateral PQ and L, we have 1, 2, 3, 4 rectangles. Therefore, quadrilateral PQ and L must be also a rectangle. So if you don't found that the big quadrilateral PQLN is a rectangle. So in total we have 3 rectangles. This is a rectangle. So it has 4 rectangles. So in the next step I'll copy this big rectangle PQLN in a new drawing, and we'll find out the height of this big right triangle ABC. But again, we already found out that quadrilateral PQLN is a rectangle. So it has 4 rectangles. this is rectangle PQLN, the coordinates of the original drawing. So in the next step, we join points A and P together by a straight line. And we join points A and Q together by a straight line. Actually, we already found out that PQ equals to 2x. This maximum PQ is equals to 2x units in its length. So already know PQ equals to 2x according to what we already found out. BC, of course, equals to 10 units in its length, according to what we already found out, according to the Pythagoras theorem. BC equals to 10. First of all, what is the area of this triangle, triangle ABC? The area of any triangle equals to the base of the triangle times the height over 2. We choose the base of this triangle ABC is AB. Times the height is AC because it's red line with the base. So times the height AC over 2. So if you found out that the area of this big right triangle ABC is equal to the base AB equal to the base AB times the height AC over 2. Again, found out that the area of the height AC equals to the base AB times the height AC over 2. AB 6 times AC. The height AC is 8 over 2. So in total, if you found out that we have this big right triangle ABC, it is equals to 6 times 8 over 2. 6 times 8 is 48, and 48 over 2 is 24. The area of the big right triangle ABC equals to 24 square units in its size. We can find out the area of triangle ABC in a different way. Actually, the area of triangle ABC equals to the base of the triangle times the height over 2. You choose the base as BC. The height must be perpendicular to the base. For that reason, from point A, we'll go perpendicular on BC. Well, it will be the height to the base BC. We find the touching point of the perpendicular from point A and the base BC. This point is point H. Let's point Y. Okay. So we mentioned before, AY, so this angle, we do perpendicular from point A on BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to construction. AL is the height, so AL is the height that we define the height AL as H. AL is the height of the big right triangle ABC that is equals to H units in its length according to our definition. So thereafter, right triangle ABC equals to the base BC times the height AY over 2. If you don't know that there of this triangle ABC in total equals to the base BC times the height AY over 2. ABC total equals to the base BC times the height to the base AY over 2. AY equals to H according to our definition. AY equals to H. So we substitute AY by H and get that now the ABC in total equals to the base BC times the height H over 2. And again, the outer ABC equals in total to BC times H over 2. But we found out that the outer ABC equals to 24 square centimeters, so we substitute the outer ABC by 24, and we get that 24 equals to BC times the height H over 2. Here we multiply this equation by 2, and we get that 24 times 2 is 48. 48 equals to BC times H. We only found out that the base BC equals to 10, so substitute BC by 10. We get that 28 equals to the base BC that is 10 times H. So 48 equals to 10 times H. Here we divide this equation by 10, and we get that the height H is equal to 48 over 10 is 4.8. In total, we found out that the height HY of ABC is equals to H according to our definition is equal to 4.8 units in its length. We define the touching point of the perpendicular from point A and PQ. This point is point F. Again, PQ, the base PQ of triangle APQ, this is the base PQ of triangle APQ, that is equals to 2x. So, what is the length of this small line segment FY? PQ and L is a rectangle. PQ and L is a rectangle. And then we found out that and the opposite sides of a rectangle are parallel to each other. So in a rectangle PQ and L, PQ is parallel to LN. PQ is parallel to LN. Those two corresponding angles are located between those two parallel lines and therefore are equal to each other and their sizes. So, but this angle equals to 90 degrees, therefore the corresponding angle, this corresponding angle is also equal to 90 degrees in its size. Likewise, those two corresponding angles are located between the balance PQ and LN, and therefore they are equal to each other and their sizes. So this angle equals to 90 degrees, and therefore the corresponding angle, this corresponding angle is also equal to 90 degrees in its size. AY is the height of triangle ABC, it is absolutely straight line. The height edge of triangle ABC, it is absolutely straight line. According to Olympiad, the sum of the angles on one side of the straight line is equal to 180 degrees. Which angles we have at the left side of the straight line AY is point F, we have 90 degrees, plus the missing angle, total must be equal to 90 degrees according to Olympiad. Therefore, this missing angle must be equal to 90 degrees in its size. Likewise, the sum of the angles on the right side of the straight line AY is point F must be equal to 90 degrees. Therefore, this missing angle must be equal to 90 degrees in its size. So actually, those two angles, those two quadrilaterals, they are both right angles because they have 4 right angles. Qn is the radius of the circle that is equals to x. Here Pn is the radius of the circle that is equals to x. So in rectangle PQ and Y, the opposite sides are equal to each other. So Qn equals to the opposite side Fy. But Qn is x, therefore Fy must be also equal to x units in its length. What is the length of the height AF of triangle APQ? AF equals to AY minus Fy. Again, AF in total equals to AY minus Fy. So AF in total equals to AY, that is the height of the big triangle ABC, minus Fy. So AF in total equals to AY, that is the height of the big triangle ABC, the height of the base BC. According to our definition, AY equals to H minus Fy. We just find out that Fy equals to x units in its length. So total AF equals to H minus x units in its length. The height AF of triangle APQ is equal to H minus x units in its length. AF equals to H minus x. But we only found out that edge equals to 4.8. So we substitute edge here by 4.8 and totally get that the height f of the small triangle APQ is equal to 4.8 minus x. Again, if you found out that the height f of the small triangle APQ in total is equal to 4.8 minus x units in its length. What is the area of this small triangle APQ? From the drawing, it is very easy to say that the area of this triangle APQ in total it is equal to the base PQ times the height AF over 2. And again, now this one, triangle APQ, total equals to the base PQ times the height to the base AF over 2. PQ equals to 2x times AF. AF equals to 4.8 minus x. Divided by 2. So total, we found out that the area of this triangle APQ, the small triangle APQ, equals to the base 2x times the height 4.8 minus x over 2. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. And we have to leave x times 4.8 minus x. So total, we found out that the area of triangle APQ is equal to x times 4.8 minus x. So here we'll open the brackets, this expression, and total we get that the area of triangle APQ in total it is equal to x times 4.8 is 4.8x. X minus x squared is minus x minus x minus x times minus x is minus x squared. So in total we should find out that the area of this line APQ is equals to 4.x minus x squared is in its size. In the next step, we join points B and P together by a straight line. We define the point of tendency of tangent AB. If this circle, this point L, this point O, and we join points P and O together by a straight line. Point O is the point of tendency of tangent AB with this circle. Therefore, according to 1, this angle equals to, and PO is of course the radius of the circle, is equals to x. So according to 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we define the point of tendency of tangent AC with this angle. This point is point Z. And we join points Q and Z together by a straight line. ZQ is of course the radius of this circle that equals to x. Point Z is the point of tendency of tangent AC with this circle, and therefore, according to 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So by doing all those constructions, we divided the big right triangle ABC into 6 parts. The first part is this triangle APB. This is the first part. The second part, we join point C and Q together by a straight line. The second part of triangle ABC is triangle AQC. The third part is the right triangle PBL. The fourth part of triangle ABC is the right triangle QNC. The fifth part of triangle ABC is this left triangle PQNN, and the sixth part of triangle ABC is triangle APQ. It is very clear that The rectangle ABC in total must be equal to the sum of the areas of the 6 shapes that it consists of. Again, this big rectangle ABC must be equal to the sum of the areas of the 6 shapes that it consists of. That is to say, it must be equal to this first shape plus this second shape plus this third shape plus this fourth shape plus this fifth shape plus this sixth shape. So thereafter ABC in total is equal to this first shape that it consists of, the rectangle APB, plus the second shape that it consists of, this is rectangle AQC, plus the third shape that it consists of, is actually this rectangle PLB, plus the fourth shape that this triangle ABC consists of, is actually this triangle QNC, plus the fifth shape that triangle ABC consists of, is actually this rectangle PQLN. Plus the sixth shape that it consists of, is actually this triangle APQ. Then again, the triangle ABC must be equal to the sum of the areas of the 6 shapes that it consists of. The 6 shapes that triangle ABC consists of are as follows. Consists the triangle ABP, first is triangle AQC, triangle BLP, triangle PNC, the rectangle PQLN, and triangle APQ. So in total, the triangle ABC equals to those 6 shapes that it consists of. But we already found out that the triangle ABC is 24 square centimeters, so we substitute the triangle ABC by 24. So the triangle ABC equals to the triangle APB. So this triangle APB, the triangle APB equals to the base AB times the height OP over 2. The base AB is 6, the height OP is x divided by 2. 6 times x over 2. So in total, this triangle APB equals to 6x over 2. Plus the area of the second shape, that is the area of this triangle AQC. The area of triangle AQC equals to the base AC times the height NQ over 2. The base AC is 8. The height NQ is x divided by 2. So in total it is 8x over 2. Therefore this QC equals to 8x over 2. Plus the area of triangle PLB. What is the area of this triangle PLB? It is equal to the base BL times the height LP, that is x over 2. So it is BL times x over 2. Plus the area of the fourth shape that it consists of is actually the area of this triangle QNC. The area of this triangle QNC equals to the base NC times the height NQ, that is x over 2. So in total, the area of this triangle QNC equals to NC times x over 2. Plus the area of the fifth shape, that is this rectangle PQNN. The area of the rectangle equals to the length of the rectangle times the width. The length equals to x, PQ equals to 2x, times the width, that is x. So in total, the area of rectangle PQLN equals to 2x times x. Finally, plus the area of the sixth shape, that is actually the area of this triangle APQ. We already found out that the area of this triangle APQ equals to 4.8x minus x squared. So in total, there are this big triangle ABC is equals to 24 and equals to this long equation, long expression. 6x over 2 is 3x. 24 equals to 3x. Plus 8x over 2 is 4x. So here we have BL times x over 2 plus NC times x over 2. So here we take x over 2 as a common factor from those two expressions. So what is left from this expression after we took from it x over 2? What is left is actually BL plus this expression and cx over 2. So what is left from this expression after we took from it x over 2 as a common factor? What is left is actually nc. So in total, the sum of those two expressions is equal to x over 2 plus BL times BL plus NC. 2x times x is 2x squared plus 4.8x minus x squared. So 24 equals to 3x plus 4x is 7x plus x over 2. What is the value of BL plus NC? What is the sum of those two line segments, BL plus NC? From the drawing, it is very easy to see that if you remove from BC this line segment LN, you get those two line segment BL and NC. So in total, there are of the BL plus NC in total must be equal to BC minus NL. Again, it is BC minus NL, because if you remove from BC this line segment NL, you get exactly those two line segments. So in total, we found out that BL plus NC equals to BC minus LN. BC is 10, LN is 2x. Why LN is 2x? Because in rectangle, the opposite sides are equal to each other. PQ is 2x, and the opposite side, LN, must be also equal to 2x units in itself. So in total, BL plus NC equals to BC that is 10, BC that is 10, minus LN that is 2x. So in total, the sum of those two lines equals to 10 minus 2x units in itself. So BL plus NC equals to 10 plus 2x units in its length plus 2x squared plus 4.8x plus x squared. So in total, 24 equals to 7x of this expression. You open the brackets of this expression and you get that 10 over 2 is 5, so total this expression equals to 5x plus we have minus 2x times x over 2. Minus 2 over 2 is 1, so we're left only with minus x times x, that is minus x squared. plus 2x squared plus 4.x plus x squared. So 24 equals to 7x plus 5x is 12x. Here minus x squared is minus 2x squared, and minus 2x squared plus 2x squared is 0. So those three expressions will get cancelled. And we're left only with 4.8x, because 7x plus 5x is 12x, so in total we found out that 24 equals to 12x plus 4.8x. This is the value of the expression in this side of the equation, and this equals to 24, of course. So 24 in total equals to 12x plus 4.8x. What is left on this side of the equation is only 12x plus 4.8x. So in total, we should know that 24 equals to 12x plus 4.8x. And again, we should know that 24 equals to 12x plus 4.x. 12x plus 4.x, 12x plus 4.8x plus to 16.8x. In total, we should find out that 24 equals to 16.x. 24 equals to 16.8x. Here we divide this equation by 16.8. And finally we get that x, that is the radius of this circle, of those two circles, is equal to 24 over 16.8 units in its length. We would like to find out the area of this green shape. For the ball, it is very easy to see that the area of this green shape in total equals to the area of the big right triangle ABC, or the area of those two small circles. Okay, we already found out that the area of this big right triangle ABC equals to 24 square inches in size, plus the area of those two small circles. The area of any circle equals to pi times the radius of the circle squared. The radius of each circle is x, therefore it is pi x squared. But because of the fact that those two circles are identical, they must have also the same areas. Therefore, the area of those two circles in total must be equal to the area of one circle, that is pi x squared times 2. So in total, if you found out that the area that we are looking for in the equation, that is the area of this green shape, is equal to the area of the big right triangle ABC, roughly 24 square inches inside, minus the area of the two small circles. The area of the two small circles in total must be equal to 2 times the area of one circle, because they are identical. And the area of one circle equals to pi x squared. So in total, the area of the green shape equals to the area of triangle ABC, that is 24 square inches in size, minus the area of the two circles, that is 2 pi times x squared. So it is 2 pi times x squared. X is 24 over 16.8, and therefore x squared must be equal to 24 over 16.8 squared. So total there the Green-Shell equals to 24 minus 2 pi times 24 over 16.8 squared. So it is 24. What is the value of this expression? This expression in total equals to 12.823. The total there of the Green-Shell equals to 28 minus 12.823 is actually 11.177 square is in size. And that's up to the second question. And again, I should find out that there that we're looking for this question. That is, there this Green-Shell is equal to 11.177 square in size. So we finish with the second question. In the next step, I'll start the lecture. I'll start with the first question, of course. Our task in the second question is to find out of this semicircle that is held by this big quarter circle AOB. This is a right angle. Again, AOB is a right angle because AOB is a quarter circle. In addition, we know that this is the small line segment OS that equals to 3 units in itself. Okay, again, in the drawing, you have a quarter circle AOB. This is the right angle because AOB is a quarter circle. Inside this quarter circle, we have this small semicircle. This is line segment OS that equals to 3 units in its length. In addition, we know that RKQ equals to RQB in its length. Again, our task is to find out of this small semicircle. So, in the first step, we define the center of this semicircle. This point is point C. And we find the touching point of the semicircle with this big quarter circle. This point is point P. And from point C, we define the point of tendency OB with this semicircle. This point is point S. Likewise, so point C is the center of the semicircle. Point S is the point of the semicircle itself, because point S is the point of tendency of tangent OB with this semicircle. So point C is the center of the semicircle, point S is the point of the semicircle itself, therefore CS is the radius of the semicircle, is equal to R according to our definition. Okay, so in the next step we did a construction, that is to say, from this point Q we do perpendicular on OB. Again, from point Q we do perpendicular on OB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and OB. This point is point M. Okay. So we have here this angle equals to 90 degrees, this angle equals to 90 degrees. According to rule 1, of course. Those angles are defined as one-sided interangles, and according to rule 22, if the sum of two one-sided interangles is equal to 180 degrees, then they must be located between parallels. That is to say, CS is parallel to LM. So I can click on rule 2. According to rule 2, if the sum of two one-sided interangles is equal to 180 degrees, then they must be located between parallels. We have line A and line B, and the red line C cuts those two lines A and B. Those two angles, alpha and beta, are defined as one-sided interangles. And if the sum of those two one-sided interangles is equal to 180 degrees, that is to say, if alpha plus beta equals to 90 degrees, then they must be located between parallels. Then line A is parallel to line B. So we can implement rule 22 in our drawing. When the sum of those two one-sided interangles is equal to 180 degrees, therefore they must be located between parallels. That is to say, CS is parallel to LM, according to rule 22. Likewise, the sum of those two one-sided interangles is equal to 180 degrees, therefore they must be located between parallels. That is to say, PO is parallel to CS. Likewise, the sum of those two one-sided interangles is also equal to 180 degrees, and therefore they must be located between parallels. That is to say, PO is parallel to LM. So we have found that QM is parallel to CS, is parallel to PO. So all those three lines, they are parallel to each other. PO is parallel to CS, is parallel to LM. Okay, so whenever you have three or more parallel lines, and you have two line segments that cut the three parallel lines, that connects the three parallel lines, you can implement Third theorem. We have here 1, 2, 3 parallel lines. Line segment QP connects between those three parallel lines. Likewise, we have line segment OM that connects between those two, between those three parallel lines. For that reason, you can implement this theorem in our drawing. So what is the theorem? We have here PO is parallel to CS, is parallel to QT. This is line segment PQ that connects the three parallel lines. This is line segment OT that also connects those three parallel lines together. And therefore can implement in this drawing this theorem. According to this theorem, PC over CQ equals to OS over ST. Again, PC over CQ equals to OS over ST. So here, this theorem gives us the relationship between the two lines that are not parallel to each other. The lines PQ, the relationship between line PQ and line OT that are not parallel to each other. According to the relationship is as follows, that PC times CQ equals to OS times ST. So we can actually implement all this theorem in our drawing. So according to this theorem, PC or CQ equals to OS or SM. Again, PC times CQ equals to OS or SM. Again, PC or CQ equals to OS or SM. PC is the radius of the circle is equal to R. CQ is also the radius. So PC or CQ equals to R over R and is equals to OS that is free over SM that is the missing side. So if you don't know that R over R equals to 3 over SM. R over R is 1, so 1 equals to 3 over SM. Here we multiply this equation by SM, and we know that SM equals to 3 units in its length. This is the answer at SM, that is equal to 3 units in its length. So, in the next step, we join points O and Q together by a straight line. By joining points O and Q, get it the right triangle OMQ. We know that RKQ equals to RQB in its size. This is the angle POQ that's obtained on RKQ. Likewise, this is the angle QOB that's obtained on this RQB. And because of the fact that those two arcs are equal to each other in their lengths, we have all 23 that state that if two certain angles subtend on equal arcs, they must be equal to each other and their sizes. Those two certain angles subtend on equal arcs, that is to say AQ and QB, therefore must be equal to each other and their sizes. Point O is the center of the quarter circle. Therefore, those two angles are defined as certain angles because their vertices lie on the center of the circle, the quarter circle, at the center of the circle. So those two certain angles subtend on equal arcs and therefore they must be equal to each other and their sizes. So repeat quickly on all 23, according to all 23, certain angles that subtend on equal arcs are equal to each other and their sizes. So in the drawing, we have a circle. This is center angle AOB. Point O is of course the center of the circle. Center angle AOB subtend on RKB equals to 100 degrees in size. Likewise, center angle COD subtend on arc CD equals to beta degrees in size. If arc AB is equal to arc CD in its length, then those two certain angles that subtend on equal arcs must be equal to each other in their sizes. That is to say, alpha equals to beta. So, as I mentioned before, because of the fact that those two certain angles subtend on equal arcs, that is to say, AQ and QB, they must be equal to each other in their sizes. So, if we define the size of this certain angle as alpha, the size of this angle, if we define the size of this angle Q is theta, then the size of this angle QOB must be equal to beta, therefore to theta, because they are equal to each other in their sizes. So theta plus theta equals to angle OB is 90 degrees. So theta plus theta equals to 2 theta, and 2 theta equals to angle AOB is 90 degrees. So 2 theta equals to 90 degrees, and therefore theta equals to 90 degrees in size. This is again theta, because again theta equals to 45 degrees in size. So this is angle theta that equals to 45 degrees in size. This is again QOB is equals to theta, and theta equals to 45 degrees in size. So in total, we found out that angle QOB in the right triangle QM equals to 45 degrees, angle QM in the right triangle QM equals to 45 degrees in size. In the next step, we focus on the right triangle QOM. The right triangle QOM, tangent and tangent 45 degrees equals to QM over OM. Again, tangent 45 degrees in the right triangle QOM equals to QM over MO. In the right triangle QOM, tangent 45 degrees equals to QM over MO. QM is the missing side of verticity. Here, OM equals to 3 plus 3, that is 6. OM equals to 6. So, OM equals to 6. So in total, tangent theta equals tangent 45 degrees equals to QM over 6. Tangent 45 degrees is 1, so in total, function 1 equals to QM over 6. If we multiply this equation by 6, and find 1 QM equals to 6 units in its length. This is answer at QM, this equals to 6 units in its length. What is the length of line segment LQ? Actually, we did another construction, that is to say, from point C we go perpendicular on QM, and then from point C we go perpendicular on QM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and QM. This point is point L. When doing the construction, we created there quadrangle CL and Q. Quadrangle CL and Q, we have 1, 2, 3 angles. And therefore, this surface angle also equals to 90 degrees inside. The formula to the rule, and the sum of the angles in any quadrangle is equal to 360 degrees. So quadrangle CL and Q is CLMS is 4 degrees, and therefore quadrangle CLMS is a rectangle. But we know that the opposite sides of a rectangle are equal to each other. So in rectangle CLMS, side SM must be equal to the opposite side CL, but SM is 3, therefore the opposite side CL must be also equal to 3 units in its length. Likewise, according to the symbol, in the same rectangle CLMS, side CS must be equal to the opposite side LM, but CS is out, therefore the opposite side LM must be equal to R units in its length. What is the length of LQ? LQ equals to QM minus LM. Q equals to QM minus LM. So QL equals to QM, that is 6, minus LM, that is also. In total, QL equals to 6 minus R units in its length. In the next step, I copy the green right triangle QLC and implemented the Pythagoras theorem on this green right triangle QLC. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Okay. This is the right triangle QLC, that the point from the original drawing. This right triangle QLC, according to the Pythagoras theorem, QC squared, that is the square of the hypotenuse, must be equal to QL squared plus CL squared. QC is out, therefore QC square is R square, and it equals to QL square. QL is 6 minus 1, therefore QL square is 6 minus R square, plus CL square. CL is 3, therefore CL square is 3 square, that is 9. So in total, R square equals to 6 minus R square plus 9. Here we open the brackets of this expression and find how that R square equals to 6 minus R square. 6 minus R square equals to 6 square, that is 36, plus R square minus 2 times 6 times R, that is minus 12 R, plus 9. We have R square on both sides of this equation, so R square will get cancelled. So in this side of the equation, we have something, that is to say 0, equals to 36 plus 9 is 45, minus 12R. So in total, 0 equals to 45 minus 12R. Here we add 12R to this equation, and find out that 12R equals to 45. Here we divide this equation by 12, and found out that the radius R of this semicircle equals to 45 over 12. 45. We divided both the numerator and the numerator of this number by 3. 45 over 3 is 15, 12 over 3 is 4. So in total, R equals to 15 over 4 units in its length. Our task is to find out the area of this semicircle. We know that the area of any semicircle equals to the area of the circle over 2. The area of the circle is pi r square. The area of the semicircle must be 1 to pi r square over 2. So it is pi over 2 times R squared. R is 14 over 4, so therefore R squared is 14 over 4 squared. 14 over 4 squared. So in total, the semicircle equals to pi over 2 times 14 over 4 squared. 14 over 4 squared. 14 squared is 225, 4 squared is 16. So in total, this expression equals to 225 pi over 2 times 16. 2 times 16 is 32. So in total, the semicircle equals to 225 pi over 32. 225 pi over 32 equals to 22.09 square centimeters. So in total, we should find out the area of this semicircle. It is the area that we are looking for in this version. It is equal to either 425 pi over 32 square centimeters. In terms of numbers, the area of this semicircle is equal to 22.09 square centimeters. So we finish with the first question. The next step, I present it to the second question. So I'll click on the solution of the second question of this section. In the second question, our task is to find out the area of this green shape. But again, in the second question, our task is to find out the area of this shaded area. So, in the drawing, we have the right angle ABC. This angle is a right angle. You know that side AB of triangle ABC equals to 6 units in itself, side AC equals to 8 units in itself. The hypotenuse BC is the missing side. Inside this right angle ABC, we have those two identical circles. And again, our task is to find out the value of this shaded area. In this case, the test is to find out the value of this green shape. So first of all, we found out the loop of the hypotenuse BC. According to the Pythagoras theorem, BC squared, that is the square of the hypotenuse, equals to AB squared plus AC squared. It's entire BC squared, that is the square of the hypotenuse, equals to AB squared plus AC squared. BC is the missing side, so it is, and it is equals to AB square. AB is 6, therefore AB square is 6 squared, that is 46, plus AC square. AC is 8, therefore AC square is 8 squared, that is 64. So in total, BC square equals to 36 plus 64, that is 100. BC square equals to 100. So here we took out all to this equation and found out that BC equals to the square root of 100, that it's 10. The hypotenuse BC equals to 10 units in its length. In the next step, we found out the area of this right triangle, triangle ABC. The area of any triangle equals to the base of that triangle times the height over 2. We choose the base of that right triangle as AB, so it is the base AB times the height AC over 2. Right triangle ABC equals to the base AB times the height AC over 2. AB is 6, AC is 8 over 2. 6 times 8 is 48, and 48 over 2 is 24. So in total, we found out that the area of the right triangle ABC equals to 24 square centimeters. Then we calculated the other right triangle ABC in a different way. The right triangle ABC will be equal to the base the triangle ABC will be equal to the base BC times the height to the base AY to the edge over 2. Again, the triangle ABC equals to the base BC times the height to the base that is edge over 2. And again, the triangle ABC equals to the base BC times the height to the base AY over 2. So it is the base BC times the height, we define AY's edge, so it is the height edge over 2. BC is 10, so we know that the outer BC is 24, so 24 equals to the base BC times the height of edge over 2. Again, BC is 10, so subtract BC by 10. But if you found out that 24 times 2 equals to BC, that is 10 times h. So 48 equals to 10h. 48 equals to 10h. Here we divided the equation by 10. If I found out that h, that h of triangle ABC equals to 48 over 10 is 4.8. So if I found out that the height edge to the base BC equals to 4.8 units in its length. In the next step, we define the center of this again, this point as point Q. Define the center of this again, this point as point Q. Define the point of tendency of tangent AB with this second, this point is point Q. Define the point of tendency of tangent AC with this second, this point is point Z. Define the point of tendency of tangent BC with this second, this point is point M. Define the point of tendency of tangent BC with this second, this point is point N. And join points P and N together by certain. We define the radius of this second as X. We join points P and N together by certain. Point P is the center of the second, point N is the point of the second center, for P is the radius of the second, that is X. The radius P is 1 to point N, that is the point of tendency of tangent BC with this second. And now radius that is 1 to the point of tendency, then tangent BC will be perpendicular to the radius LP. If BC is perpendicular to LP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to 1. Likewise, join points Q and N together by certain. Q is the radius of the second is X. They are identical, therefore they have the same on the eye. So Q is the radius of the second is equals to X, and this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we find the touching point with this between those two circles. This point is point F. From point F, we do perpendicular on BC. Again, from point F, we do perpendicular on BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. What is the definition of line segment FL? FY. What is the definition of line segment FY? FY is a common tangent that belongs to both angles. Fy is tangent to this second at point F, and Fy is also tangent to this second, the same point F. So Fy is a common tangent that belongs to both angles. So the radius QF is 1 to point F, that is the point of tendency of tangent YF with this second, and according to rule 1, this angle equals to 90 degrees. Again, likewise, the radius YF is 1 to point F, that is the point of tendency of tangent F, of tangent PF with this second. Therefore, according to rule 1, this angle equals to 90 degrees. So in total, in quadrangle PFYL, we have 1, 2, 3 right angles. This is quadrilateral PMZN. Okay. We do from point M perpendicular on BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. Those two angles are both right angles according to rule 1. So in total, in quadrilateral PMZL, we have 1, 2, 3 right angles. Therefore, this 4 piece angle must be equal to 90 degrees in size. Likewise, in the small quadrilateral MQNZ, we have 1, 2, 3 right angles. This angle equals to 90 degrees according to rule 1. Therefore, this 4 piece angle must be equal to 90 degrees in its size. In those two quadrilaterals, we have 4 right angles, and therefore they are both rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle PMZL, side PM equals to the opposite side LZ. So PM is X, the opposite side LZ must be also equal to X units in its length. Likewise, according to the same rule, in rectangle PMLZ, PL equals to MZ. So, but PL is X, therefore the opposite side ZL also equals to X units in its length. Likewise, in this rectangle MQNZ, MQ equals to the opposite side ZN, but MQ is X, therefore the opposite side ZN must also equal to X units in its length. So here, we can implement rule 10 in our drawing. Actually, according to rule 10, we find out that PQ in total equals to X plus X, that is 2X. That is to say, we find out that PMQ is one side line. For that reason, PQ equals to PM plus MQ, according to rule 10. Rule 10, according to rule 10, if two circles touch each other externally, then the side line that connects their circles together passes through their touching point. So in the drawing, we have those two circles. This is their touching point, that is defined as point P. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the side line that connects the circles together. According to this rule 10, the side line OM must pass through point P, that is their touching point. Again, the side line OM must pass through point P, that is their touching point. OPM is one side line. We can implement rule 10 in our drawing. In our drawing, we have the center of this circle is at point P. The center of this circle is at point Q. Because of the fact that those two circles have an external match between them at point M, it means that the straight line PQ that connects the circles together must pass from point M, that is the touching point. Or PMQ is one side line. Because of the fact that PMQ is one side line, it means that PQ must be equal to PM plus Q plus MQ. That is X plus X, that is 2X. So in total, we found out that PQ equals to 2X units in its length. PQ equals to 2X units in its length. So in the next step, I copy this rectangle PQ and L in a new page and found out the height to the base BC of the big triangle ABC. So actually, repeat again. Quadrilateral PQ and L is 1, 2, 3, 4 right angles, and therefore it is a rectangle. PQ and L is a rectangle. PQ and N is a rectangle. So this is rectangle PQ and N. So we already found out that those four angles are right angles. This is the radius X, this is the radius X. We already found out that PQ equals to 2X. Okay, so in the next step, from point A, we do perpendicular on BC. For point A, we don't perpendicular on BC, that is the height to the base BC. So AY is the height to the base BC. This angle equals to 90 degrees, this angle also equals to 90 degrees according to our construction. So the octagon ABC equals to the base BC times the height AY over 2. We define the height AY as h. AY equals to h according to our definition. And again, this angle equals to 90 degrees, this angle also equals to 90 degrees according to our construction. Quadrilateral PQLN is a rectangle. Those two, we know that the opposite sides of a rectangle are parallel to each other. So an rectangle PQLN, side PQ is parallel to the opposite side LN. Those two corresponding angles are located between parallel lines. Therefore, they are equal to each other and their sizes. But this angle equals to 90 degrees, and therefore this angle must also equal to 90 degrees according to the rule that I mentioned. Corresponding angles between parallel lines are equal to each other. Again, those two angles are also defined as corresponding angles, and they are located between the same parallel lines PQ and LN. Therefore, they must be equal to each other in their sizes. But this angle equals to 90 degrees, and therefore this angle must be also equal to 90 degrees in size. Again, this angle equals to 90 degrees according to rule 3. The sum of the angles on one side of the straight line is equal to 180 degrees. If you focus on the right side of the straight line AY at point F, then the sum of the angles must be equal to 180 degrees, and therefore this angle must be equal to 90 degrees inside. Again, the sum of the angles of the left side of the straight line AY at point F must be equal to 180 degrees. This angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees inside. So, we have the small quadrilateral PFYL is 4 right angles, and therefore it is a rectangle. Likewise, this small quadrilateral PQ and Y is also has 4 right angles, and therefore it must be a rectangle. So those are 2 rectangles, and the big quadrilateral PQ and L is also a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle PFYL, side PL must be equal to the opposite side FY. But PL is x, therefore the opposite side FY must be also equal to x units in its length. What is the rough line of the height AF in triangle QPF? AF is the height to the base QP of the small triangle AQP. Again, AF is the base to the height to the base of triangle APQ, the small triangle APQ. The base is PQ, and AF is the height to the base PQ of the small triangle AQP. Because this angle equals to 90 degrees and this angle equals to 90 degrees. What is the value of AF? For the moment, it is very easy to say that AF in total equals to AY plus minus AF equals to AY minus FY. Again, AF equals to AY minus FY. Please again, AF equals to AY minus FY. So AF equals to AY, that is h according to our definition. It is the height of the big triangle ABC. It equals to h according to our definition. Minus Fy. We just right now found out that Fy equals to x. So in total, F equals to AY, that is x. That is h minus Fy, that is x. So in total, AF equals to h minus x units in its length. Again, AF equals to h minus x units in its length. What is the value of h? Actually, what we found out that h equals to 4.8 units in its length. H equals to 4.8 units in its length. So we can substitute h by 4.8. So AF equals to h minus x, that is 4.8 minus x. AF equals to 4.8 minus x. Repeat again, AF is the height to the base PQ, the small triangle APQ. The area of this small triangle APQ must be equal to the base PQ times the height to the base AF over 2. And again, now the small triangle APQ equals to the base PQ times the I to the best, that is AF, over 2. The best PQ times the I to the best AF over 2. We already found out that the base PQ equals to 2x. Here PQ equals to 2x times the height AF, that is 4.8 minus x. And the base PQ equals to 2x, and the height to the base AF equals to 4.8 minus x divided by 2. We have 2 in the denominator, so 2 will get cancelled, and we have 2 of x times 4.8 minus x. So total, they have the small target APQ equals to x times 4.8 minus x. We open the brackets of this expression and find that the target APQ equals to 4.8 times x. X times minus x equals to minus x squared. So in total, the area of this target APQ is equal to 4.x minus x units, 4.x minus x squared units in size. The area of this target APQ equals to 4.8x minus x squared units in size. Our test is to find out the area of this green shape. What is the area of this green shape? Actually, before that, we join points P and B together by side line, we join points P and Q together by side line. PQ is the radius of the circle, this is x, and according to 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. We join points Q and C together by side line. Q and C together by side line. We join points Q and Z together by side line. Q Z is the radius of the circle, this equals to x. According to 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So what is the area of the green shape? We know that before that, we know that the area of triangle ABC is equal to 24 square units in size. The right triangle ABC is divided into 6 parts, and therefore the area, that is to say 6 parts is 6 shapes, and therefore the area of triangle ABC must be equal to the sum of the areas of the 6 shapes that it consists of. The triangle ABC consists of this first shape that is triangle APB, plus the second shape that is triangle AQP, plus the third shape that the third shape that is the right triangle PBL, plus the fourth shape that is the right triangle QNC, plus the fifth shape that is left triangle PQLN, plus the sixth shape that is triangle APQ. Therefore, the area of triangle ABC must be equal to the sum of those 6 shapes that it consists of. And we know that the area of triangle ABC equals to 24 square units in size. So the area of triangle ABC must be equal to the first shape ABP. The area of this triangle ABP equals to the base AB, that is 6, times the height OP, that is x over 2. So total it is 6x over 2. The area of the first shape that this triangle ABC consists of equals to 6x over 2. Plus the area of the second shape that this triangle ABC consists of, that is this, the area of this triangle AQP, that equals to the base AC, that is 8, times the height ZQ, that is x over 2. So it is 8x over 2. The area of the second shape that triangle ABC consists of equals to 8x over 2. Plus the area of this third shape that triangle ABC consists of. This is a right triangle PBL. Right triangle PBL equals to the base BL times the height LP over 2. PL is the missing side, LP is x. So in total, the area of this third shape equals to BL times x over 2. The area of the third shape that is triangle ABC consists of equals to BL times x over 2. Plus the area of this fourth shape that triangle ABC consists of, this is the right triangle Q and C. The area of the right triangle Q and C equals to the base NC times the height NQ, that is x over 2. So it is Cn times x over 2. So the area of the fourth shape that triangle ABC consists of equals to NC times x over 2. Plus the area of the fifth shape this triangle ABC consists of, this actually the of this rectangle PQLN. PQ equals to 2x, PL equals to x. The of an rectangle equals to the length PQ, that is 2x, times the width PL, that is x. So PL is 2x, PQ is 2x, the width PL is x. So it is 2x times x. The of rectangle PQLN equals to 2x times x. Plus the of the sixth shape that is triangle ABC consists of, that is actually the of this triangle APQ. We already found out that the of triangle APQ in total equals to 4.8x minus x squared. Of the sixth shape that is triangle ABC consists of, that is the of triangle APQ, equals to 4.x minus x squared, x in its size. So here we have 24. The triangle ABC of course equals to 24. It is equals to 6x over 2, that is 3x, plus 8x over 2, that is 4x, plus BL over 2 times x, plus NC times x over 2. So here we took x over 2 as a common factor from those two expressions. So what is left from this expression after going from it x over 2 is a common factor? What is left is actually BL. Likewise, what is left from this expression after we took from it x over 2 is a common factor? What is left is NC. So total, the value of those two expressions in total equals to x over 2 times BL plus NC, plus 2x times x is 2x squared, and we have also 4.8x minus x squared. So we have here 3x plus 4x is 7x. Here we have x over 2 times BL plus NC. What is the value of BL plus NC? What is the sum on the left of those two lines with BL plus NC? For the drawing, it is very easy to see that if you remove from BC this part, and then if you remove from side BC this part LN, we're left only with BL plus NC. So BL plus NC equals to BC minus LN. Okay. BL plus NC equals to BC minus LN. Because if you remove from BC this part, we're left only with BL plus NC. So BL plus NC equals to BC minus LN. BC is 10, LN is 2x. Why? Because the opposite sides of a rectangle are equal to each other. PQ is 2x, and the opposite side LN is also equal to 2x units in its length. So in total, BL plus NC equals to BC, that is 10, on LN, that is 2x. So in total, BL plus NC equals to 10 on 2x units in its length. Again, BL plus NC in total equals to 10 on 2x units in its length, plus 2x squared, plus 4.8x minus x squared. So here 24 equals to 7x. We have this expression, we open the brackets of this expression. 10 over 2 is 5, so in total this expression equals to 5x units in its length. And we have minus 2x times x over 2. 2 over 2 is 1, so we left only with minus x times x, that is minus x squared, plus 2x squared, plus 4.8x minus x squared. 24 equals to 7x plus 5x is 12x. We have minus x squared is minus 2x squared, minus 2x squared plus 2x squared is 0. So those two expressions will get cancelled. And we're left only with plus 4.8x. So in total 24 equals to 12x plus 4.8x. And again, in total we found out that 24 equals to actually 12x plus 4.8x equals to 16.8x. So 24 equals to 16.8x. Here we divided this equation by 16.8 and finally found out that x, that is the radius of the circle, equals to 24 over 16.8 x units in its length. Our task is to find out this green shape. from the drawing, it is very easy to see that they have this ratio equals to in total to the area of the big right triangle ABC minus the area of those two circles. We only found out that the area of this big right triangle ABC equals to 24 shown in the size. Once the area of this, the sum of the areas of those two small circles. Because of the fact that those two small circles are identical, they must have also the same areas. Therefore, the sum of the areas of those two circles must be equal to the area of one circle times 2. The area of one circle is pi x squared. Therefore, the area of two circles equals to 2 pi x squared. In total, the area of the green shape equals to the area of the big right triangle ABC minus the area of the small circles, that is 2 pi x squared. The area of the big triangle ABC equals to 24 minus 2 pi x squared. We only found out that x equals to 24 or 16.8. So it is 2 pi x squared. X is 24 over 16.8, therefore x squared is 24 over 16.8 x squared. So in total, the green shape equals to 24 minus 2 pi times 24 over 16.8 squared. So it is 24. This expression in total equals to 12.823. Now the green shape equals to 24 minus 12.823. And it actually equals to 11.177 square inside. So in total, we actually found out that the area of this green shape, that is the area that we were looking for in this question, in total it is equal to 11.177 square in size. Okay, thank you very much.